Okay, so what we want to start out with today is we're starting out with chapter 4. And we're going to be covering the first couple of sections today. I'll let you know what pages the homework's on at the end of the lecture here. We're starting to get into the dosage calculations, but there's some background information that we have to have before we can work on that dosage calculation process. Now, I'm the type of person, I prefer to not memorize formulas because I come from engineering where there are thousands of formulas, and if I tried to memorize them, there's no way I can do it. So I prefer to learn background topics and general topics and be able to get what I need from that. So you'll see my focus tends to be on some of that background information. So as we're doing our dosage calculations, I'm going to stress the background concepts before we start looking at formulas. One of those background concepts is what you got out of this last unit, the dimensional analysis. Now, the textbook gets a little overboard with dimensional analysis. Having those problems where there's like 8 different units and grams to the power of -1 and liters squared and all that stuff is kind of nonsense. I mean, there are applications where that's important, but it's way beyond what you guys need to know for dimensional analysis. The important stuff for dimensional analysis for you guys would be things like in that last page of the test doing conversions. I'm going to purposely pick one that I know isn't on the test. So you might have a pump that might be rated at 1,000 gallons per hour. And we need to know to compare it to other pumps that are rated in cubic feet per minute. So to make that comparison and make that conversion, it is actually dimensional analysis that is telling us what to do. We have 1,000 gallons over 1 hour. We turn our rate into a fraction like that. And now we have to change gallons into cubic feet, and we have to change hours into minutes. So I'm going to start out with the gallons. The gallons had to go on bottom to cross cancel, and we're changing into cubic feet. 1 cubic foot is about 7.5 gallons. So the gallons cross cancel. We now have cubic feet per hour. We want it per minute. So our next step, we're going to get rid of the hours. Since the hours are on bottom, we're going to put hours on top and convert to minutes. 1 hour is 60 minutes. And now we see that the hours cancel out. So what we're seeing here is what we have left is cubic feet on top and minutes on bottom, which is what we want in our final unit. So we can go ahead and multiply 1,000 times 1 cubic foot times 1 is just 1,000 cubic feet. On bottom, we have 1 times 7.5 times 60 minutes. Well, 7.5 times 60 is that 450 minutes? It's Friday. The internal calculator is a little slow today. So it is 450 minutes. So now that we have that, obviously we need to convert this back into what we call a unit rate. And we do that by just dividing by the number in the denominator. Kind of like reducing a fraction. So 450 minutes divided by 450 is just 1 minute. 1,000 cubic feet divided by 450 is 2.22 cubic feet. So 2.22 cubic feet over 1 minute is just 2.2 cubic feet per minute. That's a conversion that you would have to look up, knowing that 1 cubic foot is equal to approximately 7.5 gallons. So that's the equivalency, just like, 1 foot equals 12 inches or 1 meter equals 1,000 millimeters. That's an equivalency that you would have to look up. Now, that's not in this textbook. This is not units. Gallons per hour is not units we would use in medicine, but I used that example because I wanted to make sure I didn't hit something that was a problem on the test. But you can see the process is still there. I don't need to know anything about gallons per hour and cubic feet per minute. I just need to know the equivalencies to what I have to what I want to go to. Another example of dimensional analysis at work might be, let's say you want to calculate, but you don't know a formula. Let's say I want to know how long would it take to travel 840 miles at 60 miles per hour. So I want to find how long. I want to find a time here. So what I'm actually doing here is I'm combining units. I have miles and miles per hour, and I want to end up with something that is in time, so probably hours. So how am I going to get to that? Well, I can start out with my 840 miles. And kind of like what we did with some of our other measurement conversions, I can put that over 1 to make it into a fraction. Anytime we have a rate, 60 miles per hour is an equivalency. That means 60 miles is equivalent to 1 hour. So I can use that equivalency, just like I did up above here, the 1 cubic foot equals 7.5 gallons, or just the same way I would use 1 foot equals 12 inches. I can use that to convert. I'm put miles on bottom and hours on top. 60 miles equals 1 hour. And note, because the miles were on top here and I had to cancel them out. Yep. So the miles have to cancel out because I want to get rid of them. And now we've got 840 times 1 hour, 840 hours, 1 times 60 on bottom, and we can divide that out. 840 divided by 60 is what, 14? Divided by 60 is 14. So that's 14 hours that would take. Now, many of you probably know that to calculate the time to take a trip, it is the distance divided by the rate, which is basically what we did here. But if we didn't know that formula, as I said, the units tell us what to do. And as we get into our dosage calculations, that ability to just line up the units so that they cancel out saves us from having to memorize about a half dozen different formulas. Now, the next basic concept that you guys learned in the last unit was based on solutions and solution concentration. And what that concept was the amount of active substance in a solution. Now, for the most part, that amount of active substance, we're going to refer to that with the generic word serum. Serum could be a medication, a pure medication like lidocaine, iodine, anything that we would use, or it could be a sample of blood, urine, something like that. It's just a pure substance that is our active substance that we're working with. And the amount of that active substance is equal to the concentration times the total amount. Now that total amount, that total solution always contains 2 parts to it. It contains that serum, that active amount, and it contains a diluent of some sort. Dilutant's a really fancy word for an inactive substance. Generally, that diluent is sterile water. And usually for that diluent, we use saline or some sort of sterile water, which basically is the same thing. The abbreviation we're going to use for that is NS. So NS stands for, the words NS can actually be used for two different acronyms. Normal saline So normal saline means it's a solution that has no medicinal value and it is pH balanced to match your body's pH, is all that means. Or neutral solution. Neutral solution could be water, could be saline, could be anything that can be put into the body and have no interaction with the body. So it has no medicinal value again. So all it is that there is to reduce the concentration of the medication that we're mixing it with. And we use that formula in our solution mixing problems, like the last one on the first page of our test, to track the amount of that active ingredient and make sure that stays the same. That's one thing that happens when we're diluting. The amount of the active ingredient has to stay the same. So what we're going to talk about today, the first thing we're going to talk about is something called a dilution. And a dilution is taking that active ingredient, taking a serum, and diluting it with some sort of inactive, sterile water, normal saline, whatever. The way a dilution would be stated is usually something like this. We might have a 1 in 6 dilution. So what that means is we have 1 part of serum compared to 6 parts of total solution. Well, how would that work? Well, let's look at some examples of this. Let's say that we have 20 microliters of serum dissolved into an 80 microliter solution. What that means, our dilution there, remember dilution is serum to total solution. So as we're making this dilution ratio, do we know the amount of serum? 20 microliters. Do we know the amount of the total solution? Yeah, the 80 milliliter solution implies that's the total solution. So 80 microliters. So the microliters as a unit cancels out, and we're left with 20 over 80. We're going to reduce that like we would any other fraction. Both of those will divide by what number? 10 will work. 20 divided by 10 is 2, and 80 divided by 10? 8. Are we done there? One more step. Yes, they can both divide by 2. Makes it a 1 to 4. So that is a 1 to 4 or a 1 in 4 dilution. Let's go the other direction with that. That's the answer. For us to find, I didn't write down, but I asked you to find the dilution. Yeah. So that is a 1 in 4 dilution. If I ask you, how much of a 2 in 7 dilution can be created using 60 milliliters of serum? So again, I'm starting out with a dilution. And again, I always label these out just so that I don't lose track of them, but we have the top number, the first number in the dilution, the 2, represents the amount of serum. The 7 represents the total solution. Yes. So now, do we know the amount of serum? 60. You bet. So we set up a proportion, and on the other side, the other ratio, we match up the 60 milliliters with the 2 because both of those represent the amount of serum. What we're going to find down here, of course, is going to represent what? Yes, the amount of total solution. Is that what we're looking for? How much of this dilution can be created? Yes. It's worded a little funny, but that is asking how much of this solution can we create? So that is what we're looking for, is the total solution. So we're going to cross multiply and divide. 7 times 60 divided by 2 is 210 milliliters. So 60 milliliters of serum would enable us to create 210 milliliters of total solution in a 2N7 dilution. So that's using the straight dilution ratio. Now, when you look at ratios, there's something we have to look at. Let's say for this class, we're going to compare students in Richmond to students at Rice Lake, the number of students. Let's see, how many are over in New Richmond, by the way? Was it like 13 over there? 9 right now? All right, let's say there's 10 of them. 9? Okay, we do 9. So there's 9 students in New Richmond, and I know there's 1 missing here in Rice Lake, so there's 6 in Rice Lake. So that's a 9-to-6 ratio. We can reduce that, of course, dividing by 3, gives that a 3-to-2 ratio. But there are other ratios hidden in that ratio. I could create the ratio of New Richmond students to total students for the course. Well, how many students are in New Richmond? Still 9. How many total students would be in the course? Perfect, 15. If there's 9 in New Richmond and 6 at Rice Lake, that adds up to, I don't know why I wrote 16, it adds up to 15 total. So the ratio of New Richmond students to total students for the class is 9 out of 15. Or I could also create the ratio of Rice Lake students to total students in the class. Yeah, 6 out of 15. 6 students at Rice Lake, 15 total. And notice that adds up. 9 plus 16 is where we got the 15. So let's bring that concept back to our dilution. Let's say we have a 1 in 5 dilution. We know that 1 represents the amount of serum, the part serum, and the 5 represents the parts of total solution. The question is, how many parts of saline would be included in that then? If there's 5 total parts, and 1 of those parts is serum, there's 4 parts. You got it. 4 parts of saline. Those have to add up. The parts of serum and the parts of saline have to add up to the total. So if I'm looking at a dilution ratio for a 2N9 dilution, what is the ratio of serum to saline? So we have our dilution, which is 2 out of 9, 2 to 9. Well, again, let's label it. That 2 represents the parts of serum. The 9 represents total solution. That's not the ratio we want. We want the ratio of serum to saline, not serum to total. So if I have serum and saline, how many parts serum are there? There's still 2 parts serum. How many parts of saline would there be? You got it. 9 minus 2 gives us 7. So the ratio of serum to saline would be 2 to 7. Oops, is there a question, Richmond? Okay. So the reason we're doing that, the reason we're creating that ratio of serum to saline is because often when we go to mix one of these dilutions, we need to know those ratios. Now there are other ratios here. There could be a ratio of saline to total solution as well. And that ratio would be, well, now the total solution is still the 9. The saline is that 7 parts. Again, if there's 9 total parts in the solution and 2 of those parts are serum, it's 9 minus 7 to give 7 parts of saline. So let's look at an example. How much saline would be mixed with 60 milliliters of serum to create a 3 in 10 dilution? So again, we're going to start with that dilution, 3 in 10. Now again, I'm going to label it. The dilution is always the top number, the 3, is the parts of serum. The bottom number, second number, is always the total parts of solution. But what we have in our problem is we have the serum and we're looking for the saline. So for this problem, we need a ratio between serum and saline, NS. So that ratio, again, the part serum is still 3. That doesn't change. If there's 10 total parts in the solution, if 3 of those parts are serum, how much is saline? 7. 10 minus 3 is 7. So the ratio of serum to saline would be 3 out of 7, or 3 to 7. So to finish off the problem, we have 60 milliliters. What does that represent? The serum. So that goes on top with the serum. You have to make sure those match up. And then we're going to cross multiply and divide. This number is going to give us the amount of saline. So 7 times 60 is 420. Divided by 3 is 140 milliliters. That is the amount of saline that would be needed. We should always go back and double check and make sure we answered what the question was asking. And here the question is asking how much NS, or how much saline, would be required. So 140 milliliters is the amount of saline. Let's ask how much saline would be needed to create those 720 milliliters of a 1 in 7 dilution. So once again, we start out with our dilution. That is 1 in 7 ratio. What does the 1 represent? The part serum. What does the 7 represent? The parts of total solution. So now in this problem, we are given the 720 milliliters. What does that represent? That is of the 1 in 7 dilution. That is the total. That represents the total. Are we looking for the amount of serum? No, we're looking for the amount of saline. So we need to keep the total solution. What we really need here is a ratio of saline to total solution. So in this ratio, the total solution is still 7 parts. That hasn't changed. If one of those parts is serum, how many parts are saline? 6. 7 minus 1 gives us 6. So the ratio of that solution is 6 parts saline to 7 total parts. And now we can put in the 720. Whenever it says so many milliliters of a 1 in 7 dilution or whatever dilution it is, the dilution is referring to the total solution. So that 720 is our total solution. We cross multiply and divide. 6 times 720 divided by 7 is going to be an ugly number. 617.14 milliliters. So it takes 617.14 milliliters of saline to create that 720 milliliters of total solution. Now, if this idea of creating this other ratio is giving you trouble, sometimes we can get away without changing it. Then this is a problem where we could do that. We could have used this dilution here, the 1 in 7 dilution. And we could have used the 720 milliliters of total solution. If we cross multiply and divide there, 1 times 720 divided by 7, we're going to get 102.86 milliliters if we round it off. But what does that 102.86 milliliters represent? Yeah, it represents the same as the 1 does, which is the amount of serum. So if we wanted to know the amount of saline, we would have to subtract. There you go. Our total solution of 720 minus 102.86, and that will give us the 617.14. So in this problem, that would work. But there are other problems where that won't work. I might ask, how much of a 1 in 6 dilution can be created using 450 milliliters of saline? So if I write out the dilution here, that's 1 in 6. The 1, of course, represents serum. 6 represents total solution. Well, the only amount we're given in the problem is the amount of saline. That doesn't represent either one of those numbers. So here I can't use this ratio because neither one of those amounts is given in the problem. But I can create a new ratio. Now I want to know how much of the dilution, right? So am I looking for the amount of serum or the total solution? Remember, whenever we say the amount of the dilution, that is the amount of the total solution that's referring to. So how much total solution can be created? So what we have, we're given the saline and we want to find the total solution. So what we'd really like to have here is that ratio of saline to total solution. Well, our total solution is still 6 parts. That doesn't change from over here. If one of those parts is serum, how many parts are saline? You got it, 5. 6 minus 1 is 5. So now we can write our proportion. The 450 goes with the saline on top. And you cross multiply and divide. 6 times 450 divided by 5. 540 total milliliters of solution. So these dilutions are important for diluting medications and other things. Another place where this dilution can be very important is in testing. Let's say you have a meter that maxes out at 800 milligrams per deciliter. This might be for urine testing or blood testing, depending on what we're testing. You take a sample of blood and your blood sample exceeds the limits of the meter. The meter gives you back an error, or unable to read. So what we have to do is we have to dilute that blood in order to read it. So let's say we're going to use 40 milliliters of blood with 80 milliliters of sterile water and then retest. So what we've done is we've diluted the blood so that the concentration should be lower and within the limits of our meter. Is there a question? Oops, thank you. I'm going to pause my recording for serious stuff. So anyway, thank you. So we retest, and it retests at 293 milligrams per deciliter. We want to find milligrams per deciliter. Find the true level. So find the true reading. Well, the first thing we have to do is we have to look at this here where we diluted it and figure out what was that dilution. And we have to be careful. Remember, a dilution is serum to total solution. In this case, our serum is the blood, which is 40 milliliters. Now, I always put the units in it first just to make sure the units match up. The total, however, is not the 80, it is 80 plus 40. So that's 40 milliliters over 120 milliliters. The milliliters cancel out, and that's going to reduce. Both of those numbers can divide by 40 to give me a 1 in 3 dilution. Now, that dilution ratio is also the ratio of readings. That's why we set up the dilution in that manner, as being serum out of total parts. So we can take that 1 to 3 ratio, and now we have to analyze. What's going to go up here is going to be the smaller value, because 1 is smaller than 3, and what we're going to get down here is going to be the larger value. We have that 293 milligrams per deciliter that our meter gave us. Do we expect the true value to be bigger than that or smaller than that? Well, remember, the reason we had to do it was because the meter only goes up to 800, right? Yeah, the true value is going to be bigger. This is smaller than the true value. We diluted the true value down to get it to this so that the meter could read it. So we put that 293 milligrams per deciliter on top because that's the smaller number. The true reading has to be bigger because we diluted it down. We put water in it to dilute it down, so it's going to be less concentrated. Right? So we cross multiply and divide. 3 times 293 divided by 1 gives us 879 milligrams per deciliter. So you can see that is bigger than the 800. That's why the meter wouldn't read it. The true value is 879 milligrams per deciliter. Let's do another example of that. We'll approach it from just a little bit of a different route. So once again, we're going to say the meter is exceeded. We exceeded the limits of the meter. And your policy is to perform a 1 in 4 dilution and retest. So there's going to be 2 questions coming out of this. How much NS should you combine with a 50 milliliter blood sample? So that's the first question. Then after we retest, and because we only got a couple of minutes left here, I'm going to abbreviate a little bit. We retest to get a reading of 204 milligrams per deciliter. We want to know what is the true reading or true level. So the first part, how much saline do we need to add to this? Well, it's a 1 in 4 dilution again. But remember, the 1 is serum, and the 4 is total solution. What we have is the blood, which is the serum, but we need to find the saline. So we need the ratio of serum to saline. The part serum is still going to be 1. How many parts saline? Yeah, 4 minus 1 gives us 3. So now we can find the amount of saline by plugging in 50 milliliters is the blood, that's our serum, and we cross multiply and divide. 3 times 50 divided by 1 is 150 milliliters of saline. So we combine that 150 milliliters of saline with the 50 milliliters of blood. We retested and we got that reading of 204. We used the dilution again, the 1 in 4, to adjust that reading. Where does the 204 milligrams per deciliter go? On top. And we will cross multiply and divide. 4 times 204 divided by 1, 816 milligrams per deciliter. Because we need to know how much water we had to mix in, how much saline we had to mix in with it. But when you adjust the reading, it's always back to the true dilution. Yes, because we know that number is going to be smaller than the true reading. So it has to go with the smaller of the 2 numbers in our dilution. You look really confused. Because we asked how much saline do we have to add to the blood? So we had to know how much saline to add to the blood. So we use that to figure out we're going to add 150 milliliters of saline to that 50 milliliter blood sample. Added to the, yes, added to the blood to get that diluted amount. Yes. Okay, no problem. Homework is page 130 to 132. 1 through 37, the odds. Yes, I will make sure I post it on Blackboard once I get the recording posted. You bet.